All right, here we are in part 3. We've got our normal maps and we've got an understanding of tangent space now. So let's put it together to transform our normal map out of tangent space into world space and do the lighting for real. As a review, we have 3 vectors now in model space. We have the normal vector, the tangent vector, and the binormal. And these are 3 vectors in the local model space that we have for each vertex. Now these 3 vectors, they are unit vectors and they are mutually perpendicular, so that makes an axis system, an x, y, z axis system. And we can write that as a 3x3 rotation matrix. I believe I've mentioned this before, but it's really worth stressing this because this is a great way to get a deeper understanding of what a matrix really is. Let's say I have an axis system. I have an x-axis, I have a y-axis, and then x cross y give me a z-axis. So there's my axis system, and I can rotate this to any orientation, right? And we've done this. Say this is my model space, and I want to transform out to world space. How do I do it? Well, if I make a matrix that represents this orientation, then how would I ask the question, what is the x-axis of this orientation out in world space? If I go from local x, this is my local x-axis, what is that out in world space? Well, let's do that. If I take the x-axis, that's just x, and I transform it using this matrix from local space out into world space, what do I get? Well, I get this. And what is that except the x-axis that I'm indicating here with my finger? The x-axis, as it points in world space, is the top row of my matrix. The second row of my matrix is my y-axis, and the third row is my z-axis. Now that lets me go either way. I can take a matrix and I can say, oh, this is the x-axis, this is the y-axis, this is the z-axis, and go, okay, x, y, z, and now I have an understanding of what my orientation is. Or I could go the other way. I could say, this is my x-axis, this is my y-axis, this is my z-axis, boom, I made a matrix. We can use this to apply it to our tangent space matrix. We have a tangent axis, we have a binormal axis, and we have the normal axis. And if we just say that we'll put the x along the tangent direction and we'll put the y along the bitangent direction, then cross one into the other, that gives you the normal in the z direction. We can now just stack these 3 and boom, it's a 3x3 matrix ready to roll. This is the matrix that will transform us from the tangent space given to us in model coordinates out into world space. Now let's say that a little more clearly. The object was given to us, the mesh was given to us in model space, and we were given, for each vertex, we were given a tangent and a normal, and from that got the binormal. And in the vertex shader, we transformed those from model space out into world space. So we can actually make now the tangent to world matrix using those transformed vectors. And I have here basically the steps that are required to do this transformation. When we hit the pixel shader, we are going to take as inputs to the pixel shader the normal and the tangent. We're going to get those in, and they will be in world space already. Now, remember, this was something that came up for a lot of folks on the midterm. When we get a normal, and this is true for the tangent as well, when we get them in to the pixel shader, they have been interpolated from different corners of the triangle. And that will make them no longer normal. So we will re-normalize those in the pixel shader. So you can get those 2, and then you can generate the bitangent with a cross product, right? Okay, that gives us the normal, the tangent, and the bitangent gives us that matrix. I'm calling that the TBN matrix. You just stack the tangent, the bitangent, and the normal into a 3x3 matrix, and you've got it. Next, we will use the UV coordinates that were input from the original model, and we will use those to sample the normal map texture. So we're going to look up a color from the texture using your UV coordinates. We will unbias that. Remember, we had to cram that normal into a 0 to 1 range. So now we're going to uncram it, right? So we'll convert from the 0 to 1 range into a -1 to 1 range. And now we have the normal. This is getting us the normal, but it's still in tangent space. It's just the normal that we got right out of the texture. So we will then transform it from tangent space into world space using this matrix. All right, now that we've got that, what we have is a normal in world space, boom, that can go straight into the lighting code that we already wrote, and all of that lighting code should now respect our normal map. So here we have it. I've taken all those steps and combined them, and this is what it looks like. This looks like a very detailed three-dimensional cube with sort of like a quilted cushion pattern on it. Maybe it's a couch cushion or something. But really, we know this is still a perfectly flat cube. We're achieving this illusion through normal mapping. And now that I have performed that tangent to world transformation, we are lighting it in the correct space. All of the faces are lit from apparently the same light source. And as the cube rotates, that light source holds in place so we see the lighting move across the surface as the cube changes orientation. Now this first one, I have only the Lambert term enabled. I don't have the specular on yet. So let's flip the specular on and take a look at that next. Here's that same cube with the specular component enabled, and you can see it's nice and shiny now. And that really helps to also highlight how the light is holding still as the cube is rotating. So one last demo, I'm going to hit this thing with some color. And here that is. What I've got here is 3 separate lights, and each light is a different color. So as you can see, the red light is sort of directly at where the camera is. So the red light hits the face most strongly when the face points directly at us. And there's a blue light over on the left side. So as the cube turns, it starts picking up that blue light. And we can also see the green light is shining down from the top. And that allows us to pick up those green lights when the face is sort of tilted up. But we're also now seeing those buttons in the couch cushion sort of allow us to visualize which direction is pointing upward. That'll be green, and where it's pointing to the left, it picks up the blues. And when it's pointing forward, it'll get those reds. And for a final demo, I wanted to show this. This is the normals being rendered as colors. Now, I'm not using them for lighting calculations. There are no lighting calculations here. This is just those normals that I have read in from the normal map, and I've transformed them into world space. And these are the kinds of colors that you get. This is really useful for debugging, to ask, are my normals doing the right thing? When you're trying to get the lighting to work and you can't figure out something's wrong, one good option is, just draw the normal. If you draw the normal, that helps you to understand. Like remembering that red is the x-axis, green is the y-axis, and blue is the z-axis. You can look at these colors and say to yourself, what is that normal right there? Okay, so we saw the demo. That's what it's supposed to look like if we do normal mapping correctly. And we saw some black and white, and then we put in some colored lights so you could see the different directions more clearly. This is what we're going to be doing in the lab this week. We're going to apply this technique to the platforms that our mannequin robot is standing on. So that's it for part 3. There is one more part of this lecture today where I'm going to talk about a more advanced type of concept called parallax occlusion mapping. So we won't get a chance to do that one in the lab, but let's go ahead and go through it anyway. That'll be part 4.